Thank you. So let's get started. So we'll be talking about advanced generation methods. And this is just a fun picture. It's a paradox that two hands drew each other into the life. So next slide. So what we have been doing till now in the course is we were learning about the deep learning toolbox, which is essentially deep neural network, convolutional neural network, RNN, variational autoencoders, and how to train them. So from now onwards, we'll put all these techniques into this box of DL toolbox. All are accessible to us. We can pick the way we want. Now the real question is that how can you put all of this together to do something more interesting, more fun? So this lecture's focus is really on this something extra, which is more intuitions and insights about the actual problem. And we use these techniques just as tools, and we'll see there are different ways to put these things together for different applications. So we'll be focusing on something extra. So let's ask this question, right? This is lecture about image generation. So how machines do it today? We have learned about GANs and VAEs. So they do something like this. They take a random vector of some n dimension, they pass it through a feed-forward giant neural network, and they hope to see a good image. This is sort of one-shot generation, where you take one random vector, project it into high dimension, you have trained this network well, hopefully, and you hope to see a good image. But you can see that this is not very natural, and some of you might expect that if this machine gets 2 or 3 more iterations to fix this image, then this image might start looking better. And now let's think about how do we do it. So we have pretty well-defined procedure for drawing images, right? We draw first a skeleton of what we want to draw, and here we take a decision of what we want to draw. Then we start adding details. Then we add more details, and then we get a final picture. So as humans, we iterate continuously. We focus on each subpart. We give attention to one part. We use feedback, where we take a look and we do what are the other things can be added. So we do it all this while machine does one-shot projection. So really the question of this presentation is, can we make machines do something like this? And so these methods are basically divided into 2 categories. One is pixel by pixel generation. Now the simplest way of accommodating feedback is you generate 1 pixel at a time, and you condition that pixel generation on previously all generated pixels. So this is one simple model. And then there are more advanced stuff, iterative attentive generation, where you sort of first update some abstract schema, you update it, iterate on it, and then generate a final image from it. So now I'll hand over to Anand to cover pixel by pixel generation, and I'll cover the next one.
Yeah. Okay. Okay. So the roadmap would be, first I would be talking about the intuition. Then we'll discuss the basic models of pixel RNN and pixel CNN, and then Hsiao will discuss the variants of pixel RNN and pixel CNN. Okay. Let's start with the customary cat slide. So if we see the cat slide, cat body over here, we see that most of the pixels are correlated to each other. So the question is, how do we encode this correlation in our model? So let's break this problem. Suppose say we have an n cross n image. We have an n cross n image, and let's label each pixel as x1 till xn for the row 1, and at the end we have xn square. And say we want to generate this brown pixel xi, which is dependent on all the previous pixels generated. So again we are generating pixel by pixel. We assume that this all pixels are generated. Now we want to see how we can generate this pixel. So if we model, if we model this as a joint probability distribution, we see that we can simplify this by Bayes' theorem just by factorizing this. And once we factorize this, we see that this is nothing but product of conditionals. That is, the pixels which we want to generate is dependent on all the previous pixels which are given in blue. So basically it's nothing but a sequential model. Okay. So once we see a sequential model, what comes to our mind is LSTM, which Arun covered it in the second week of this course. So, but the question is, can we use this vanilla version of LSTM to generate image pixel by pixel? One way would be unrolling this as a single row vector, that is flattening them all the vectors and then feed it into our LSTM network. But then still we are not using the spatial correlation aspect of the pixel generation. So how do we ensure that all informations are well propagated in this 2 dimension? So let's discuss a special class of LSTM, which is spatial LSTM. They are one type of multi-dimensional LSTM. Okay. So let's say we want to generate this brown pixel. Again, this all pixels are generated row by row. And we say that this pixels is directly dependent on all its neighborhood pixels generated. But this dark blue pixels in turn are dependent on this light blue pixels, which while generating these pixels, we use these pixels to generate them. Now, say we have 2 LSTM layers. So each of this is a LSTM unit. Each of this, the circle indicates a LSTM unit. So we have 2 layers of different LSTM layers, and so what we do is this is our input to state vector. That is, the features what we have for these pixels gets as input to this LSTM unit, and we also have another input, that is a feedback from the previous LSTM unit, which is acting as like a recurrent again. So this LSTM unit was particularly used to generate this pixel, and this LSTM unit was used to generate this pixel. So we are taking the output of this LSTM unit and feed it into our new LSTM unit, which we are using to generate these pixels. So in the next layer, this LSTM unit act as input to state vector for our next layer LSTM unit, and again the process repeats. So this take feedback from these 2 LSTM units. Now we put this information what we have gathered in a softmax layer. So this softmax layer has 256 channels. So it has 256 channels. Basically, it's a one hot vector encoding, and we get an output which gives us a pixel value which we want to take. So we get a distribution, basically probability distribution, and we can choose the maximum or we can sample from distribution the way we wish to. Is this clear? Is there any question about the spatial LSTM? Okay, moving on. Suppose I want to generate on next this pixel. So we move just, the process repeats the same. Now my field of interest changes. If you see that my field of interest just changes. Now I want to generate, first we generated this pixel, we got this pixel value, and we feed this again back, this information what we gathered into our input, and next we want to generate this image, this pixel. So the process repeats the same. Now my input to state vector, from input to state vector is this, all this neighborhood pixels, which takes as input to state vector. The neighborhood LSTM units gives me state to state feedback, and after that we use this input to state again for the next layer, and so on and so forth. So we repeat this multiple times to generate all our pixels. The basic idea is, this is one of, as Ameya said, this is one of the way we can generate row by row and pixel by pixel.
So how many different sets of parameters are there?
Parameters as in?
How many parameters do you have to train?
So we would have features from this one, and we would have feedback from this, say H1, and we have another feedback from this H2. So basically we are having feedback from all this as as a features, and then we have feedback, we have input from these features, and we have feedback from these features. So basically we have 4 parameters here.
Each LSTM unit is basically maybe like 384 dimensional vector, the state vector, and you can have as many layers as you want.
So all units in the same layer share parameters?
Yes.
They're identical?
They indirectly share all parameters. Like for instance, when I want to generate this pixels, it is sharing parameters from this, And this in turn is sharing parameters from these two units, and this is sharing parameters from this, and this is so.
Well, no, I'm talking about the actual weights. When you're training them, are the weights identical?
Yes, for each layer they are identical.
Yeah.
But different layers have different.
Different layers have different layers.
And what is the significance of having these multiple layers? Why do you need multiple layers?
Because we want to, as we discussed, we want to have this spatial correlation between them. How do we encode? This is just a single. In the plain vanilla version of LSTM, we had only one dimensional vector. The variance was only one dimensional. But for image, it is dependent on two dimensional. That is, we have encoding in two dimensions. So this pixel is dependent from a row, the pixel generated in row as well as in columns. So we have a two-dimensional dependency over here. That's why we need a special, like, a spatial kind of LSTMs over this.
More specifically, more the layers, more the memory you have. So authors claim that because they are increasing layers, they have a lot more memory. So if you are generating pixels towards the end, there will still be influence from pixel generated in the beginning because there is so deep structure.
So having more layers increases the effective receptive field?
Effective
Exactly.
Do you have any results kind of showing how output changes based on number of layers?
Not sure. Paper didn't really change the number of layers and show different outputs, but
They just fixed one number of layers of LSTM units and they trained it on MNIST and CIFAR dataset.
yeah. But
So they just use 2?
no, they used 12 in
They used
actual
12,
paper.
yeah.
And I think 12 was the minimum it worked because they put a lot of efforts to train the 12-layer deep network. So they use these ResNet type connections and all. So I think 12 was really necessary.
The main idea was adapted from this paper, which was used to generate a grayscale image. So the spatial. So basically, here we are. So basically, they repeat this process for red channel, green channel, and blue channel. So as to generate a RGB image. But this paper was used to generate just a grayscale image. So the main idea is coming from this paper, spatial LSTM paper.
Here's one more question.
So how do you initialize the spatial context of the solid pixel?
Yeah, that's a good question. First pixel, the authors don't talk about it. We believe it's a random initialization. So based on this, then you generate different. So they just talk about from the pixel from between layer.
Do you propagate gradients after each pixel generation or after the entire image has been generated? So when do you propagate back the gradient?
Yeah. So gradient propagation doesn't happen in image generation. Gradient propagation happens in training. And generation happens during testing. Now in training, you're not trying to generate image. You have the input image and you're trying to maximize the likelihood of that image under the model that is being trained. So they use the multimodal loss to maximize the likelihood and you compute the gradients and you propagate them back for the weights.
So they're not trying to regenerate the image in training.
Exactly.
They are trying to regenerate the image.
Okay, moving on. So details about softmax. I said there are 256 classes, so which indicates the pixel values for 0 to 255, and we get this kind of distribution. But and if we take always the maximum value of this distribution or mean value, we are going to generate same image again and again. In order to generate different images, we can sample from this distribution and so that we get different images. But those images may not be as sharp as the one which we generated from the maximum image. Okay, moving on to the first class of pixel RNN, row LSTM. So the intuition is again coming from the same what we discussed in spatial LSTM. So in their architecture, they use 12 LSTM blocks. So similar to we saw the 2 layers previously. So we have an image n cross n. Now again, we want to generate this pixel, the brown pixel, and we take its dependencies from its previously generated pixel in the same row. It's again an architectural choice to choose which neighborhood pixel you want to take. What the authors claim is, in the LSTM unit, they take feedback from the 3 neighborhood pixels generated from the previous row. So that what happens is, this this LSTM unit takes feedback, gets input from this pixel, just pixel generated from this layer. Yeah. Here, so if you're wondering, we took here 4 neighborhood pixels, and here we took just one neighborhood pixel. We are what author claim is that this LSTM unit already has some information about these pixels generated. So we don't want to feed in again the same information and again in our model and make more complex and make more to make computational efficiency. They claim that to use just this pixel, and which we feed into our LSTM, that is direct mapping to the pixel which we want to generate, and it gets feedback from these 3 LSTM units, and the process repeats so on and so forth for 12 times, and then we pass it to the softmax layer and get the value and feed it back to our image. Next we repeat for the next pixel which we want to generate. This depends on this pixel, and the process repeats. So basically, if you see, the receptive field cover is in a triangular fashion. So this pixel which we wanted to generate dependent directly on this pixel, gets connected to this LSTM unit, and this LSTM unit gets feedback from this three LSTM units, and this 3 LSTM units in turn gets feedback from its previous rows LSTM units, neighborhood pixel. So we are able to cover this triangular pixels basically. But again, we are not able to capture all the informations. This 3 and this another pixel are already generated. So we are losing some information over this. So can we come up with a better model? Yes. So they use again a new type of field that is in diagonal fashion. They take, now you get feedback from its pixels or pixels in diagonal, that is the top and the left in a diagonal fashion. You take input from the previous vector, and the state to state feedback comes from these two LSTM units, and you repeat the process. So the receptive field covered basically is this in a diagonal fashion. Now you would say that again we are losing out this information. Yes. So far we have seen in triangular we lose out this information, and in the diagonal we lose out this information. Why not just take all these elements? So they say it as diagonal by LSTM. So basically this LSTM unit gets feedback from this, the right one. Now you can see that the feedback is coming from right to left. Previously we were getting feedback from left to right. Now this LSTM unit gets feedback from right to left, and this gets from right to left, and it's just the reverse process. So basically this LSTM is capturing much information as compared to all these LSTM units, and it passes this information to this. And to optimize this diagonal LSTM, one easier way would be, say we want to generate this pixel which is dependent on all these elements, that is of the diagonal dependent on these elements on the left top diagonals. So one smart way would be, which tried one pixel by one unit with respect to its previous row. Like, so this is my first row, we keep it as it is. The second row we shifted by one pixel, and the third row we shifted by 2 pixels. And what this helps us is, we can parallelize our computation. Basically this 2 pixel just depends only on this pixel, and this 3 pixel depends on this 2 pixels. So we can train this network in a column wise fashion. So this speeds up the computation, and it makes more efficient training process. Now Hsiao would discuss pixel CNN. Yeah, this is what this line indicates. So this red line indicates this is a pixel to pixel mapping, and here this 2 pixels indicate this.
So I'll be talking about how pixel CNN works and the variants of these 2 basic models. And so after we see how pixel RNNs work, we see that pixel RNNs take 2 inputs. First, it takes input from previous layer, and then they take a state-to-state input from its current layer. Okay. Sorry. So pixel CNNs only take inputs from one space. It only takes inputs from the previous layer because we want to simplify the whole structure, because recurrent neural networks take too much time to train. So what we do is that we only take if we want to generate this brown pixel, we just take input from its previous layer, the neighbor pixels in the previous layer, and so on and so forth, and we can get this pixel generated. And how we implement is we just do like a two-dimensional convolution on previous layer, like how normal convolutional structure does, and we add a mask convolution on the convolution kernel, so that we don't see the future pixels. Yeah, and that is how we keep this sequential order same as the pixel RNNs. So, is there any questions here? Okay.
The only difference is we are not getting state-to-state feedback as we were getting in RNN. So we are getting feedback from LSTM neighborhood LSTM units. Here we are able to generate from the convolution itself. So this information, the sequential information is preserved by the special masking convolution.
Yeah. Yeah, so basically they have like more layers than pixel RNNs. They have, so for the same data set, pixel RNNs have like 12 layers, and they have like 15 or, yeah.
15
But,
yeah, 15
but
convolution layers.
I don't see why you think that number of layers should be equal to the number of pixels in the image. Why is that the case?
Because for every layer, you are trying to use the neighboring
Yes, yes.
neighboring pixels to generate a pixel, right? To generate a pixel value, you're using the same value. So
Yes.
for every iteration, for every layer of the CNN, if you don't have the previous pixel values, how will you generate the current pixel value?
Okay. Well, it's a bit difficult to understand your question, but let me try to give some indication. So there is only one network, okay? There is only one network that takes some pixels in the image and gives you next pixel, okay? That's the basic idea. There is one network. You have to generate n square pixels. You do it sequentially. Every time networks takes some pixels in the image and throws out you next pixel, and that repeats, okay? So it's your choice which pixels to feed to this network, okay? And now natural images have this spatial correlation, so typically you tend to choose 1 in the previous and 3 in the top. Correct. So number of layers is independent of number of pixels, because you can choose network as deep as you want. Still, it is doing one thing. It is taking some generated pixels, throwing you out next pixel. Again, taking some generated pixels, throwing you out next pixel.
I think what she means that is because the receptive field comparing to the previous two approaches is not as large as like the right one. So this have the full dependency receptive field, and so this only takes like 4 pixels in the under layer. Yeah, so basically we need more layers for this structure. Yeah. So I'll do a little.
Yeah.
Yeah. So a little comparison between these 3 structures we discussed so far. Pixel CNNs has the fastest training speed because we can parallelize this convolution very quickly, and the 2 recurrent neural networks has a slower one. But because of the full dependency field I've mentioned here, the Pixel RNN one has much better results in their evaluation results. Yeah. And in their actual implementation, they add residual connections because there are too many layers. And they also add this channel mask because they want to generate a pixel channel by channel, which means generating the red channel first, and then the green one, and then the blue one. They just define it. There's no...
Actually, you can generate in any order. If you first take red pixel, then while generating green pixel, you condition on red. And while generating blue, you condition on R on G.
But the different channels, different color channels don't contain the same amount of information. I forget which one it is. I think the green one, usually I think is supposed to contain the most information. Or you could do like a transformation
Yeah.
two other channels.
makes sense.
So you mean there are theoretical results which say that natural images?
Theoretical, but based on human research.
Oh, I see. I see. So green contains most. Okay.
Yeah, the paper first starts
Doesn't
with
do.
red, then they move on to green, then blue.
Yeah, maybe it's a good improvement.
It seems like an obvious thing to try to first get a generated one.
Yeah.
Yeah.
But also, if we see the joint distribution of RGB and we factorize it, we get this. We take whatever the joint probability would remain same. Whatever we take pixel at a time, green
I
or
mean, in principle, it doesn't make a difference, but in practice.
Yeah. Right. Yeah.
So this is how the structure works. So the first input image goes through this convolutional layer, and then it goes through like 12 or 15 layers of recurrent layers or convolution layers, and then it goes through this softmax to compute the final output.
Oh, question.
Here. If you're generating an image, basically it's just some like random inputs, random features, or a blank out input. Yeah. And these are the results of this generation method, and they use bidiagonal LCM, which has a full receptive field model. Yeah.
Yeah. Training. So training is not that different.
Same as I discussed in spatial LSTM, right? I mean, first you have multiple images. You feed all images at a time, and you get some output, and then you backprop it. You observe output. Output is the image.
Output is the probability distribution
Yeah.
of the pixel values.
Output is essentially likelihood. Think VAE, same. It's the output is likelihood distribution.
Exactly.
Yeah, yeah.
The inspiration is drawn from language modeling, spatial LSTM. It comes from language modeling.
Questions? Okay.
Well, I guess I was going to ask, does this predate GANs and VAEs?
Oh, I'll compare them at last after I discuss this.
But chronologically,
Yeah, it does, right?
Yeah.
Yeah.
and also I should point out that this is sort of a classical method that's
Yeah.
been used since, at least 2000, but probably earlier. That's
Yeah.
how we generate textures, just
Yeah.
generating pixels one at a time in scan order, conditioning on the neighborhood you're
Yeah.
going to generate.
Yeah.
So it seems like they're just repeating the script with a trace on it.
Yeah, and with neural network, they basically brought in the neural network. Yeah.
So I'll be talking about like two variants of these two basic models. The first one is that we want to keep the global structure of an image. So we invent this multi-scale pixel RNNs. So basically what we do is that we just subsamples from the input image, and so these pixels subsample are shaded in light blue color, and we add these subsampled pixels into our deep structure deep neural network input, and we just train it. So in result, it captures like better global information. So we can see in result, it is more globally coherent. So in the left-hand side is from normal pixel RNNs, and the right-hand side is from a multi-scale one. So we can see that the left-hand side images are more noisy, and the left-hand side has a more global. Wait.
Oh, battery on.
So in the right-hand side, there is a more globally coherent structure. But for evaluation, the results are similar. So the other variant is that when we want to generate an image based on some information we have. So if we have some like image description vectors, we call it H here. If we want to generate the image based on this vector, what we need to do is to add a conditional vector here. And what we do implementation is we just take these additional input, the vector, into our deep structure as an additional input, and we just train it. So this vector can be some like one hot like class definition or a high-level image description embedding. And another case is that when this new vector has contained some location information, we first go through another deconvolutional layer to estimate another image size vector, and we feed this image size vector into the deep structure we've talked about before. Any questions here? So these are the results of conditional image generations, and the first one, also these two images are constructed by some class definitions. So there are like different classes in ImageNet dataset, and so it is just a one hot vector. Yeah.
So we design edge, right? It's our choice how to design edge. Yeah.
So whatever I do something between an elephant and a cat, will it generate a hybrid? Like intuitively, why should we just stick to one hot encoding? It's like learning a semantic space for you.
Yeah, I mean, I guess, yeah, question is, why is this better than just separately training a network to generate each class? Does it share information?
If you train it on like multiple classes together, you can generate in one class by itself.
I would argue, first of all, if you train unconditioned network, then you have no control what it will generate. First. So, but you want network to do something useful. I mean, okay, once you generate good images, you want it to be able to control it. So, first conditioning comes in that place. Like when you want to generate elephants, network generates elephants.
Yeah, but then I can just train it only on elephants. And it'll
No,
generate
ideally you would like to train one network that works for elephants, cats, dogs, cars, right?
So you're giving.
Yeah, but I guess.
How any different from a latent space of a variation autoencoder? How like what you're learning is edge that is similar to.
No, you are not learning edge.
No, I mean say that you're finding mapping a given edge to an output, right?
Yeah.
And you're trying that for given condition on a particular edge, you give this kind of output, right?
Yeah.
That's very similar to what we did in generative models. Right?
Yes, that is true. But in VAs you have a latent space defined, and so for each image you have well-defined code. Here there is no such case. Here all you have is just edge. You don't have that latent space and low-dimensional code of the image, which we saw was useful for image editing and etc.
But I guess somewhere inside the model has to learn something.
Yes, it exists, but it's not accessible to you.
Yeah, so I mean, I think it's a very interesting question. If you give it as input, kind of, a vector that has, 0.5 for one class and 0.5
Yeah.
for another, will it generate something interesting?
Yeah, that's
Yeah.
a good
Field is learning much more than just n different neural networks in some sense. It's learning transition between them.
possible. Yeah.
I mean, I guess we don't know, but it would be cool.
Yeah.
Yeah.
But I think authors didn't try that. Maybe because it didn't work, but
But I mean, I would hope basically training one network to generate all the classes somehow works better because it sees more data.
oh, I
But
see.
it's unclear.
Can I make a question? So how to generate background that is common for all the classes, right?
That's another good question.
So these basic information can be shared, like if you're training them jointly.
Yeah.
But exactly how it shares seems to be unclear.
These are some of good research problems.
So there are like three other recent improvements. We will not go into details here. So the first one is the gated pixel CNN. So what they does is it's from the same group. It's from Google DeepMind. What they do is they just improve their pixel CNN by removing some blind spot problem and replacing the activation units.
So the receptive field of the previous RNNs were on the top left, on the left and the top, right?
Yeah.
Here you're looking ahead of, like you made it a sequential problem first, and then you're again making it a non-sequential one. Is it like now it's not an RNN, like which is generating sequence?
I think it is not offense the sequential definition because I didn't include it. But actually, they just the weights for these subsampled pixels are different from the weights for these like normal structures.
So the light blue is telling how you subsample. And on subsample, you run same sequential model. So the dark blue is telling you what the sequential model. Yeah.
Like the light blue overlaps with the dark blue.
Yeah, so in subsample, you only take those where light blue overlaps with dark.
Okay.
Because we have not seen the white images,
Exactly.
it has not been generated.
We haven't even seen that.
So the second one is Pixel CNS plus. So if you're interested in how to optimize these structures, you can go see this paper from OpenAI. And the last one is video pixel networks. So they extend this work to 4 dimensions. So they add a time dimension for this work. Okay. So this is a brief comparison between the GANs and the VAEs. So these 3 are all image generation models. And so we call our models autoregressive models because they take inputs from themselves. So in terms of training, they have like the most simple training comparing to GANs, and also they are very inefficient during sampling because we have to generate the images pixel by pixel, while these 2 approaches can generate the whole image at once. And to compare with VAEs, we cannot generate some low-dimensional codes for an image, like the latent vectors for an image. So we cannot like do adjustments on images or something like that. And for results, we can see that GANs has the most sharpest results, and VAEs has the blurry ones, and our models has some kind of in middle ones. Any questions here?
Do the pixel RNNs and pixel CNNs ever have the problem where they just start generating garbage? Because it seems like they could, start generating some bad neighborhoods and then that doesn't get worse.
Yeah, if you see the results, I put it above here. If you see it like in details, there are some kind of garbage. But if these results are taken from conditional generations, so these don't seem like that garbage-like.
It is dependent on how you initialize the first pixel. That's the question. We don't know what the first pixel is. So if we take some garbage, then the next pixel generated might also be garbage, and the process would repeat.
Do they discuss this in the papers?
No, they
That's
didn't.
our intuition. It's not discussed.
Okay, so I'll hand on to Ameya.
Okay, so I'll discuss now the iterative attentive generation. So what you have seen previously is first pixel by pixel generation. Now, in some sense, this is suboptimal, correct? Because every inference decision happens at pixel level, and it's a little bit unnatural also. This might be subjective, but and second, we know one-shot generation, but we discussed why we don't like it, because it seems rather difficult to generate complex images in single projection. And especially if you have multiple objects, then you would like to take one more iteration to align those objects properly. So we want to do something different. So to find out what is different, let's go back to basics. The human way. We understand how people generate images. So this is the flow. Let's pick 3 key attributes that enable us to follow this flow. First is attention. We can focus on one part of image and develop it. So if you want to develop face, you can only look at this face and keep refining it, and you don't worry about how the legs positions are, for example. Second is iteration. All of us use multiple iterations, multiple strokes. Sometimes we erase. And third is feedback. So we draw, then we say, take a look, that how does it look? And then we kind of get intuition that something needs to be changed. So there is some feedback loop. Then the question is, how can we enable machines to sort of generate using these 3 attribute processes? Idea is draw. So this was the first paper, I believe, which attempted. So you can see that now it is generating MNIST, but its strokes are pretty human-like. So the red square is where machine is currently drawing. So it draws sequentially, just like human would have drawn strokes. So Now first question is, we said 3 attributes, correct? First question would be, how do you employ attention? Now we have to define what is attention. So attention is basically ability to focus on any one part of image and then to just modify it or understand it better. So for example, if I'm given this image, I can pay attention to face, and that will call a glimpse, and it's 60 cross 60. Obviously this is a smaller image because you're focusing on one small part. So for machine, it's basically a process of this glimpse extraction. Now how do you employ attention? There are 2 types. One is read attention. You just want to focus on some part of the image, but do nothing. So this is something like this. You throw in input image, there is some block which does it, and it gives you back the extracted glimpse. So it decided to focus on this red dot. Obviously the other type is attentive write, where you only want to modify sub part of image. So basically this was then modified as ellipse, and then there is some block which wrote it exactly at the same, more or less at the same location. And notice that the green remained unchanged, although it's slightly moved in my, but technically it should remain unchanged. So read attention. Now let's go in details of what happens inside that block. So you have input image. One operation you could do is basic filtering, because we do filtering pretty well. So you have A cross B image. You define filter size n cross A and B cross n. Then matrix wise algebra is clear that output will be n cross n. Then you define these filters to be Gaussian, so that it will be highly non-zero at some part and 0 everywhere else. More like, so, and the choice of this y1 and x1, where you choose them to be non-zero, allows you to focus and move your attention. So it's a very, and this, because this bell-shaped curve, you get a sort of linear increase or decrease in zoom. And so these 2 are the Gaussian filters. Then question will be, who decides these mu y's and this sigma and all? They are learned. Because we have neural network, we can put one more layer just to learn them. Now what happens when you try to do something like this? This is the impact. So you have this original image. Now there is one parameter I didn't discuss in previous slide, and that is this stride delta. So how much field of view you want to cover in that n cross n window. So delta is exactly like stride in your convolutions. So you basically get the subsampled version of image. So higher the slide, you get more view of image in the same size, n cross n size. And so you can see this, if the delta is small, then you get good focus. If delta is large, you get entire view. And sigma sort of controls the blur. If sigma is small, then it's pretty sharp. If sigma is large, it's pretty blur. So now we have pretty flexible model, and our machine can read, at least, yeah, that till now we only learned to read. And as I discussed, these mu i's, the means are learned, and this delta also. So any questions? Okay, so, oh yeah. No, I mean, it's just some image. I mean, my image only has 2, red dot and green dot. It's just an image, example image. Yeah. Wait, sorry, I moved ahead. Okay. So now the question is, how do you write back? Answer is, do same process. Just transpose the 2 filters. So you take n cross n, you have A cross n and n cross b, then you will get A cross b. Again you define same Gaussian, so that only in this image, only this part gets here, while this part, I mean, updated image, this part remains unchanged, because some of them will be 0 out. But the filter parameters for write and read will be different. So the operations are identical, but the parameters will be different. Okay? So now, so we are trying to basically enable machines to generate images just like us, and we have succeeded in attention. We know how to read attentively and write attentively. Next question is, how can machine do iteration? And, oh sorry, how can it do feedback? So iterations, you can argue that machines iterate all the time. I mean, one for loop is an iteration. One processor keeps iterating. For image generation, you need something to iterate upon. You need something to modify a canvas. So a canvas is some abstract matrix that you modify, that a machine modifies, keeps modifying, and typically it is chosen of the same size as that of original image. And then your final image is of some function of this canvas. And next question is, how do you employ feedback? RNNs, the deep learning toolbox, which we know can take care of the feedback. But we want to generate images. So we need variational autoencoder type. And so why don't we combine these two? So this answers Shashank's last class question, that can VAs be combined with RNNs? Yes, and that's what we are doing here essentially. And so you put all of this together, you get a final architecture that looks something like this. So you have input image, you read it, you do attentive read, then this is a conventional variational autoencoder. Remember, it is operating on a glimpse because this read operation gives glimpse. Then you do write operation, and this is your canvas. So you keep updating canvas. And there is RNN, so you put this entire structure in the feedback. And then this is the feedback loop. So what all we achieved is we finally get a posterior probability distribution for the input image if we run through all iterations. And that is our basically generation part. And that we achieved by taking sigmoid, element-wise sigmoid operation of our canvas matrix. Okay, so are there any questions? Yeah.
How does it decide where to read?
Yeah, so you can see that for read there is a feedback from decoder RNN. I have more better picture on next slide. But so this is also trained how to learn where to see.
But there's no direct supervision.
No, it's no direct supervision. That's a good part of this one. Yeah. Okay, so training procedure. What is our goal in training? We want this network to reconstruct the input image. So that's our goal. And since there is RNN, we have T iterations to do so. So let's start step by step. So for every iteration T, you take your latest canvas, which is a matrix. You compute error image first. So you see what is missing in canvas compared to X. And that is your error. Then you do attentive read of error image as well as X input image. And this is controlled by your decoder state. So the parameters in the attentive read process are decided by this decoder state, previous decoder state. So you got your glimpse. Then there comes encoder RNN. Standard feed. Right now you just evaluate feed forward path. You update its state. Then you sample. Standard variational autoencoder. You updated the state. Now you sample the latent variable Z. Then you have decoder RNN. Then you do attentive write. Again, that attentive where to write is controlled by this decoder state. And this is your same latest canvas, and then you get updated canvas. And then you keep repeating this for T iterations, hoping that eventually final canvas looks something like input image X. And so any questions? So that makes it clear that loss function should be how well I'm doing about generating this canvas given X. Correct? So we have this term here, which is same negative log likelihood reconstruction loss in VAs. And because we have this VA regularization term, which is basically KL divergence between my posterior and my prior over the latent space. But remember, we have T iterations because this is RNN. So we have to add for all iterations this loss. So recall VA lecture. It's exact same structure and exact same reason. And typically you choose this to be Gaussian with zero mean, like identity matrix variance. And this is also Gaussian with means and variances controlled by your encoder state. So I think, yeah.
On the previous slide, the error image
Yes, it's pixel-wise subtraction.
If you have pixel shifting, like we had in last lecture, you have problems of large potential.
That's true. That's true. But then I would argue that even this term also we saw previously that this term also falls like pixel difference. That's true. That's one issue. I agree. But yeah. But here I would argue that if there is because we have T iterations, initially if there is any shift, the network will try to shift it, move the little canvas and slide it. But so write operation, initial write operations are large, so it will try to shift it. So, but yeah, that's a good point. Anything else? So now we understand training well. And so given an input image, the compute T iterations in feed-forward part, you compute final loss function, you compute the gradients, propagate them back, and for propagating them back, you have to use the same trick, reparameterization trick, as you saw in VAs. But this is pretty standard stuff. So how do you test? While testing, there is no encoder, just like variational autoencoders. You start with prior distribution and you just sample Z. Oh. Then you pass it through the decoder RNN, compute feed forward, update its state. You take latest canvas, do attentive write of the canvas, update the canvas, and this keeps repeating for T iterations. That's it. And then if the network is trained well, then this will give you the generated image. A very good looking generated image. Yeah.
How do we decide the number of iterations to do?
That's a design parameter. The paper says that it's a design parameter. They typically chose 32, 64 like that. So, yeah.
How do you control what you are generating? Conditional
Yeah, here they don't control, but same model can be used to do so. We'll see down the line in the slide. But yeah, this work you have no control.
So there's no attentive read here?
Yeah, while generating image, there is no attentive read because you are generating just with prior. We will come to that. So there is a way to do this generation while reading some image. Exactly, that's the part following. I mean, towards the end we'll see that. So there is a way you can do this. Yeah.
We don't give it an instruction of moving the pencil like this. We just give it the final image and it automatically learns to move the pencil like this.
Exactly. Exactly.
Is it possible to generate latent representations of a new image? So like in VA, it is possible to get a latent representation.
Yeah.
And these are somewhere like part of this entire network.
Exactly. Yeah. So yes, it is possible, and we'll see next work exactly does that. It uses same model and tries to learn the latent space, and there's cool application for that. Yeah, we'll see. Nice. It is, but here we are not using it, right? We are just using this deep model to generate images. So although you could have learned the latent space and mapping of input image to latent space, here it is not being used. So in the next paper they use it actually. Okay, so next, okay, so now we have cool video. Oh. Okay, it somehow doesn't allow me to. Can you see it? No. What? Yeah, that's what I'm doing, but then it is only playing on my screen, so. Huh? Yeah, I tried dragging both sides, but it doesn't show. Huh?
Okay, let it.
Who's coming? Wait. Ah, yeah. Nice. Thanks. Yeah, I was worried it will again go wrong. Yeah. Wait. First, let me try something. This is good, right? So this is reading. It is reading right now. So it's a green block box shows that it is reading. Now it is generating. So see, it is writing. Notice that initially it writes a large image and then slowly it starts focusing on one stroke. Here it is generating 2 digits. Cool, right? Yeah. Yes. So when it updates canvas, it might erase something that it has previously written. But again, you are not controlling it. It just network decides to return on it. Yeah. MNIST and then SVHN and then CFAR10. I'll show those results too. Yeah. Oh yeah, perfect. Yeah, thanks. So these are the MNIST results, and these are the network parameters. So and every encoder and decoder are one layer RNNs with this many the units of H, and then this is your latent space dimension, and someone is asking how many iterations, right? So number of glimpses is number of iterations. So it's typically 32 or 64, and these are the window sizes that you pick for read and write. Now, if you see CFAR10 results, they're still pretty blur. I mean, remember we at least I was hoping that they generate more sharper because they do it over T iterations. But anyway, so to answer your question, they tried CFAR10. That's it. No, the idea is you give that huge data set to machine and leave it alone for 24 hours, and it learns on its own where to should be focusing. Yeah. Yeah. And yeah, exactly. Huh? Yeah. True. Yeah. Yeah, that might be possible. Yeah. 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 It learned automatically. Yeah. Okay, I didn't write this paper, so. No, not here. Next they will try to do. Yeah. That's possible. That is actually true because in later papers they use different attention mechanisms. That's a good point. Yeah, that is true. Oh, they use spatial transform networks directly. So they move away from this filtering and they put again a spatial transform network there. Okay, they didn't try on CFAR10, so I'm not sure. And this is the difference between with attention and without attention. So you can see without attention you just blur and then suddenly everything starts becoming clear, while with attention you're sequentially updating. Okay, so now we have one model, deep generative model, which employs this attention iteration feedback. Now for remaining time we have two goals. One, slightly improve it and then use it for two different applications. One is image compression and another is one-shot generalization. So let's again start from basics. So you have this generation flow, correct? We understand this, and this is how we generate images. There is some sort of conceptual hierarchy in these 4 images. What do I mean? For example, this image just tells you that it is some bipedal entity. This says there is some human-like being, but it could be anything. This tells there is a young boy sitting, has some hair, wearing shirt, shoes, etc. And you can go on. And this is the final exact image. So conceptually, these images have different content. Now, so you can think about it. So given this image, if I can figure out what are these three, then I'm sort of conceptually compressing it. I'm getting rid of some of these details like what is the shirt and what is shoe and whether it has hair or not. And I'm just storing human-like being. If I'm okay with this, this is kind of compression, correct? So conceptual Rossi compression, this is the question given for can machine infer 1, 2, and 3. And the reason is you will need less bits to store 1, 2, and 3 compared to 4. But there is loss. So 1 can also mean some skeleton, which is no way close to your actual image. 2 can mean Deadpool, because this is actually loss in conventional sense, because you compressed using this, but you generated this. And this is very much possible, because this image doesn't have any more information. 3 can mean something, but with different shirt color or different shoe type, etc. But 4 is the actual image. So idea is we have to pick what is the essential information and let the generative model generate the details. But the philosophical question will be, how do you define what are the details and how do you define what is essential information? For example, here, whether it's a boy or Deadpool was in the details, and essential information was that some human-like being. So this paper tried to do that. It's the same model, same team, but you can see that here you can identify what is a car model. You can maybe read the text, but as you start compressing, here you can just recognize it's some car, and you have no clue what the text is. Okay, so we have learned this deep generative model, correct? Inference model starts with input image. Quick recap. You do attentive read. You do a forward pass of RNN. You sample. You have this latent variables. Generative model, you start with latent variables, pass through decoder RNN, do attentive write. Oh, sorry. That's it. And you get updated canvas. So we are clear on these two models. Now, how do you use this for compression? Train a deep generative model for t iterations. Whatever we had, you train it for t iterations. Once you're done, give a new image x, which you want to compress, and run only t store iterations. For example, you don't run total t, you only run t store iterations, and capture all these latent variables that you got. And to go back to Hsiao-Ching's question, so here you're explicitly storing, and idea is to store these latent variables, and these variables actually represent the compressed image. So here you exploit the fact that you have this relationship, and then you can store these variables. Then question will be, okay, if I have this, how do I reconstruct? So you start with these, run first store iterations deterministically. By deterministically, I mean there is no sampling. You have the stored variable values. You just run all feed-forward passes. Then you run remaining iterations while sampling the latent variables. Important thing to note here is that the prior of these sample latent variables is dependent now on this decoder state. While in conventional VAEs, this prior is typically just Gaussian with zero mean unit variance. So this is where it sort of forces the generated latent variables to be of same content, similar information as you had stored. And then you hopefully get final reconstructed image. And I pointed out the prior here depends on this. This is important, yeah.
So in this case, are the encoder and the decoder trained simultaneously, or is the T iteration model trained first?
No. You train both of them simultaneously. This split between iterations you only do in test.
No, not, I mean like, so go back to your previous slide.
Okay.
The first slide where you introduced the thing.
Yeah, here.
Yeah, train a deep generative model for T iterations.
Huh.
Is that done first and then the decoding part, or is that trained at the same time?
No, yeah, here deep generative model, both encoder and decoder are trained at the same time for T iterations. Yeah, for many samples. Yeah.
So T is that like the maximum?
Yeah, T is the maximum. And that's a design parameter. You first define what is a T, and T store is always then less than T. Yeah.
So if I want a d-dimensional latent vector for my image,
Yeah.
will I fix my z?
No, so look, here we never discussed what is the dimension of Z. Each Z is a vector. So that's still independent.
If my downstream application, I want a d
Yeah.
for an image
Yeah.
which captures the latent space.
Yeah.
Will I use this d by d store, d by d?
Yeah. So you will have each dimensional vector for each iterations. You store how many t store iterations you want. So total number of real numbers you will have is d times t store, and those many numbers represent your compressed image. Yeah.
Do they actually evaluate on some downstream application? These latent.
What do you mean downstream?
So I mean, using BGNet, we can get a latent representation for an image, right? Which I can use in other applications.
Oh. I see. No, no, no. They are not doing that here. Because they have their own encoder to learn that latent representations. So they did not use VGG to extract first.
Well, I mean, you should show what they actually evaluate.
Yeah. So just quick details. This is the loss function, same as before. Only new parameter is beta, where you kind of weigh the reconstruction loss. And that allows you to control the pixel level reconstruction. So how much emphasis you want to put on pixel level information. And these latent variables can be further compressed using arithmetic coding or any coding technique that you may have. So this is the result. So they evaluate. This is the omniglot data set, which is basically there are many more classes and much lesser samples. But I think that is not. So here t store they varied 1, 4, 7, 10, 13, 16, 19. So you can see that initially it's pretty random. There's no way. But as it comes to 25, it's pretty good at reconstructing. But here, and the reason these strokes are very varied is because here they are sampling from this distribution. So there is some sampling, so there is some randomness. So you could go wrong. Yeah. Whoa, nice question, and I don't remember. But I think those details are in the paper. I don't remember on top of my head. Yeah.
So the sampling for T greater than T STR,
Yeah.
does it use the same encoder network from the training stage, or how do you use this prior now?
Yeah, exactly. So first of all, the prior depends on decoder previous state. So in generation, there is not really encoder. You have stored latent variables.
For only STR.
Yeah, for only STR.
What about the later?
So remember, for generation, we only run decoder with the prior distribution. Typically, prior is independent, like some Gaussian distribution. Here, that is dictated by the decoder previous state. That's it.
There has to be a neural net again which takes this previous state and puts the samples out. Right? That's the decoder.
That is the decoder, and that's how you train it.
Yeah.
Decoder is the generator.
Decoder is the generator, yes. And this HD denotes the mean of this distribution, which is again small neural network, which is a linear transformation. And then you sample with this mean. Yeah. And this is the reconstructed. These are, I think, ImageNet, some modified ImageNet data set. But here, remember, here they have generated without prior variance. So they are not really sampled, the remaining latent variables. They are only computed just deterministically with mean. So that's why here there are some random shapes, while here there is no randomness. It just gets blurred out. No, I mean, it looks like that. We are. I agree with you partly because they put a very big aim and then what they achieved is not so high, but still it's a good attempt. Yeah. So you can see here they control bits per image, but you can see that JPEG is pretty bad, standard compression engine. Here JPEG is very bad, but if you sample from there with prior variance, you get some artifacts. Without prior variance, you get blurred images. This will be clear here. So you can see here, they control bits per image 460. So JPEG is not doing good job. With prior variance, you get slightly sharper images, but you get these artifacts. And because there is some sampling, so something is random. And here, it's all clean, but they look more blurred because there is no sampling. And you can keep doing this, but when bit size image starts increasing, their quality increases, and they claim that it is remains better than JPEG, but it's subjective. Yeah. And this is one simple thing they tried is that if you weigh less on reconstruction loss, then these images appear very blurred, this sharper. Again, it's a subjective, so let's move on. Now one shot. So again, going back to this question, can you use this generative model to generate what you want? And that one way of doing it is one-shot generalization. So train your machine, again for t iterations, then give it a new image, which is not part of training image. And then ask this question, can it generate these samples? So this is one-shot generalization. I just showed one sample, and machine generated multiple of samples of the same character. And humans have this ability. We can, just looking at once, we can draw. So this is the paper they tried, which is similar to conditional generation, I would argue. And okay, this might be annoying now. That this is recall of how we generate, and I think we all are pretty clear, yeah. Yeah, so this is not one-shot learning. This is one-shot generation. So the learning is not one-shot. You consume a lot of data to learn. But the generation is one-shot. The samples that you want to generate, you have only seen them once.
No, I mean, in training,
Yeah.
anyway, you haven't seen this tested data. It's just like you input some data you never seen.
No, the other generative models, for example, if you want it to be able to generate elephants, you have to put some elephants in the training. It will generate different elephants, I agree, but you have to put some elephants. Here, you train it on dog, cat, car, whatever, and then you show it one elephant, just one elephant. Then you show it just one elephant picture. That is not part of training set at all.
Yeah, so that's what I mentioned. In training, you never saw the picture of an elephant, right?
Yeah, for classification also that's true, I agree. This is what.
Here, the bridge is like you also mentioned classification. I mean, here it is only a generative model. Like you can generate any pictures you want. So this is called a Z-space.
No, you can generate any pixel that you want, even if you have not seen even similar pictures in your training data.
So what you are mentioning two things: similarity and class label.
Yeah,
So when you're talking about the elephant, you already have the class label.
yeah, yeah,
Little bears on that. So it's
yeah.
not elephant. It's not something like you don't know what it is. Right?
Yeah.
So I mean, you can. A better example. I don't like this name. I mean, this should not be called a one shot.
Okay.
This should be called something like you just generated an asymptotic image. That should be.
Yeah.
In a training data, I mean, if you only see the picture like a dog, a sheep, or goat, and other things, you never saw anything looks like the elephant or anything looks like a goat. That should be fine. So in this case, like you saw, we never saw elephant. When you ask the machine, like you never saw elephant, or in the training set, you already have some latent knowledge, like this is the label. This is the label. It's called elephant.
Yeah.
But I mean, like this should not be called one shot. I mean,
Okay. Okay. No. I see.
Yep, disclaimer, we have not written this paper.
Yeah, we can take it offline.
Why
Yeah.
don't you just show the
Yeah.
results?
Yeah. So this is here. So we have learned this model. Now only thing we'll see is how to employ this conditioning. So for one-shot generalization, we are given this new image X. Model exists. Now we do attentive read of this image. Once, I mean, we keep doing it for t iterations, and parameters of this attentive read are controlled by this decoder state. So based on its training and iteration number, it knows where to look, and this is conditioned on this glimpse is fed to decoder RNN. Just concatenate the vector with input this latent vector. That's it. So we are not going further details. And these are some of the results. So this is the new example that was given, and the network generated multiple samples of the same example. And here, referring back to the question, so here they use spatial transform networks for attention, while previously we were using Gaussian filters. But so this I think works better. That's it. So it brings us to summary. So we have seen one message that we wanted to get across is that deep learning tools can be put together in many different ways. And what we have learned till now, they are just tools, but it's open to our innovation and novelty to how to put them together for many different applications. And second is, this presentation, we just saw essentially an extension of conventional generative models which do one-shot generation, where all these models employ some sort of feedback, some sort of RNN, and do it over multiple iterations. That's it. Thank you. Yeah, we have backups. Yeah, and the topics we didn't cover: image style transfer, I mean, it's already time. So, and one question you may ask is, we combined VIE and RNNs. Can you do with GANs and RNNs because GANs are better? Yes, you can. We have backup slides. You can take a look. Okay, thank you. Done.
always say that, right? Oh,
this one has